This video covers grounding and bonding of electrical systems for the Texas Department of Transportation. Grounding and bonding play an important role in electrical safety, and we must ensure that all electrical installations have been properly grounded and bonded. In this video, you will learn the importance of grounding and bonding to protect people from electrocution, and how grounding and bonding protects electrical equipment from damage caused by short circuits, ground faults, and overloads. This video will also describe grounding systems and components, and how they are to be installed and inspected. TxDOT engineers and inspectors ensure that work on the contract is fulfilled completely, properly, and safely. The inspector acts as the eyes and ears of the engineer on a work site. Item 5.10, Control of the Work, from TxDOT's Standard Specifications for Construction and Maintenance of Highways, Streets, and Bridges, states that the inspector is an authorized representative of the engineer. If the work does not conform to the specifications, the inspector must report it to the engineer. The inspector has the authority to reject materials or suspend work until the engineer can decide the question at issue. However, in no case will the inspector act as foreman or perform other duties for the contractor, nor interfere with the management of the work. Grounding details are shown in the plans, the electrical standard sheets, and the standard specifications, and are based on the requirements set forth in the National Electrical Code. Opening the latest edition of the National Electrical Code to 90.1, Purpose A, Practical Safeguarding, we read, "The purpose of this code is the practical safeguarding of persons and property from hazards arising from the use of electricity." The NEC has many rules for grounding electrical systems. The inspector should obtain a copy of the current edition of the NEC and study Article 250, Grounding and Bonding. TxDOT's electrical standard sheets contain a vast amount of information about TxDOT electrical systems and specific requirements that the contractor must follow. The inspector should read, study, and be familiar with these valuable resources. Until a new inspector gains a solid understanding of electrical inspection procedures, a knowledgeable person should accompany him on several inspections. By accidentally touching a live conductor, he could be seriously injured or even killed. When working on electrical systems, it is very important to wear proper personal protective equipment. For more information, refer to the Occupational Safety Division's Electrical Safety Program. The inspector must follow proper lockout and tagout procedures before conducting an electrical inspection, turning off power sources, and attaching locks and tags to prevent equipment from being energized while the system is being inspected or worked on. Whenever possible, electrical systems should be turned off before inspecting or working on electrical equipment. A voltmeter in good working condition should be used to check for the presence of voltage and to verify equipment is de-energized. Since traffic signals are necessary for traffic safety and cannot be turned off, they must either be inspected prior to energizing or else special procedures must be followed. Remember, safety first is a must, not an option, and good inspections are essential to ensure the safety of persons and property. The Texas Department of Transportation requires proper grounding and bonding of all types of electrical installations. This video will cover grounding of the following items: roadway illumination poles, high mast poles, roadside flashing beacons, pedestrian crosswalk poles, traffic control cabinets, traffic signal poles, metal conduits, electrical services, and ground boxes. The public regularly comes in contact with many components of an electrical installation, such as luminaire poles, signal poles, pedestrian push buttons, ground boxes, and traffic signal controller cabinets. Opening the National Electrical Code to Article 100, Definitions, we read the word ground is defined as the earth. Grounding is the intentional connection of an electrical system to earth. TxDOT requires an equipment grounding conductor to be installed in all conduits. All non-current carrying metal parts must be bonded together to ensure a low-impedance conductive path of electricity to earth. The grounding system creates a path to carry current from a ground fault in the wiring system back to the source of the electrical supply. This activates an overcurrent protective device and removes power from the circuit. Let's look at grounding for the protection of people from electrocution. Grounding the metal parts of the electrical system creates an intentional low-impedance path back to the electrical service and its overcurrent protective devices. Circuit breakers are the main type of overcurrent protective device that TxDOT uses. A circuit breaker protects the electrical circuit from damage caused by too much current flowing in the circuit. Current is defined as the flow of electrons. If we look inside the breaker, we can see its components overheat when too much current flows in the circuit. High current can cause the insulation on electrical conductors in the circuit to melt. A breaker acts as a temperature limiting device for the circuit. If too much current flows in the circuit, the breaker opens the circuit, stopping the current flow and protecting the conductors and equipment. Electrical conductors intended to carry electricity are insulated. Electrical conductors used for grounding can either be insulated or bare. We can identify a grounding conductor by the color of its insulation. Both TxDOT and the National Electrical Code require grounding conductors to be either green insulated, marked with green tape, or bare copper. Grounding conductors are not to be confused with white insulated grounded or neutral conductors, which carry power in the circuit. Note that the definitions of grounded conductor and grounding conductor have different meanings. A grounded conductor is defined as a circuit conductor that is intentionally grounded. The grounded conductor is intended to carry circuit current and is identified with white insulation or white marking tape. In TxDOT electrical systems, the grounded conductor is also commonly called the neutral conductor. A grounding conductor refers to what is defined by the NEC as an equipment grounding conductor. The equipment grounding conductor is part of the ground fault current path and connects metal parts of the equipment together and to the ground bus. The equipment grounding conductor is intended to only carry current during a ground fault and is identified with green insulation, green marking tape, or as a bare copper conductor. In this animation, we can see a representation of electrical energy moving in the path of an electrical circuit. Electrical power cannot be seen, heard, or smelled, yet if we touch an energized conductor or metal part, it can kill us. Now, let's trace the normal path of electricity in a typical roadway lighting installation. First, we see electrical power coming from the power lines, down the conduit, through the meter base, and into the service enclosure. From there, the path goes through the breaker, through the circuit conductors, and to the luminaire. It then follows a reverse path on the other conductors back to the service enclosure, up the pole, and finally back to the power company's lines. A conductor's insulation can be damaged by physical impact, abrasion, or by high voltage that breaks through the insulation. When the exposed copper wire beneath the damaged insulation accidentally touches a grounded metal part that is not part of the circuit, it is called a ground fault. Let's see what happens when a conductor's insulation is damaged and the energized conductor contacts the metal pole. Notice how the equipment grounding conductor provides a low impedance path for electrical current back to the breaker. The current is very high when the conductor contacts the pole because it bypasses the resistance of the light fixture in the circuit. The high current travels through a coil in the breaker and creates a magnetic field. Force from the magnetic field pulls a switch in the breaker to open the circuit, stopping the flow of uncontrolled electrical energy. Now, we will identify the real-world grounding components of a typical electrical service on a TxDOT roadway. This includes the service entrance conductors, the grounded neutral conductor, the ground bus, the grounding electrode conductor, and the grounding electrode. The three conductors at the top of the service are the service entrance conductors. One service entrance conductor is a grounded or neutral conductor. This conductor must be insulated and is always marked white. The service conductors run down the metal conduit riser and continue through the meter base. From the meter base, the neutral conductor connects to a ground bus. The ground bus is the point where several grounding and grounded conductors connect to the electrical system. From the ground bus, a number 6 solid, bare copper grounding electrode conductor connects to the ground rod or grounding electrode. This directs ground fault currents into the earth. Notice the clamp on the ground rod. This is a special type of clamp made of copper or bronze and is listed for direct burial. TxDOT specifies copper-clad ground rods. Ground rod clamps are listed for direct burial since they are installed underground. A steel clamp would rust in the moist earth and provide a poor electrical connection. The ground rod should be checked for proper installation. A small shovel can be used to remove dirt and access the connection. The NEC requires that the grounding electrode at an electrical service be at least 5/8 of an inch in diameter and at least 8 feet long. All 8 feet must be completely driven into the earth. If dirt or concrete splatter is on the ground rod, the contractor must remove all non-conductive substances before connecting the grounding electrode conductor to the rod with the clamp. The bottom end of the PVC conduit must also be in the earth and covered with soil. Another type of grounding electrode TxDOT uses is called a concrete-encased grounding electrode. A concrete-encased grounding electrode is created when the steel rebar in a concrete foundation is connected to the anchor bolt assembly. Special mechanical connectors rated for concrete encasement and a stranded copper bonding jumper are used to internally connect the rebar to the anchor bolt assembly before the concrete is placed. Concrete-encased grounding electrodes are used in steel pole and steel frame supports on electrical services, luminaire poles, traffic signal poles, high mast poles, and other places as called for in the plans on a TxDOT project. To ground an electrical service mounted on a steel service pole, the pole must be connected to the grounding bus with a 6 AWG solid bare copper grounding electrode conductor. The conductor exits the bottom of the service enclosure through a small hole and is mechanically connected to the steel pole with a tank ground fitting. The tank ground is installed approximately 4 to 6 inches below the service enclosure. The steel pole becomes the grounding path to earth through the anchor bolts. The anchor bolts are bonded to the steel in the foundation, which creates a concrete-encased grounding electrode. In the foundation, a bare copper conductor connects the rebar cage to one of the anchor bolts. This conductor is called a bonding jumper. The NEC defines a bonding jumper as a conductor that ensures the required electrical conductivity between metal parts that are required to be electrically connected. A bonding jumper ensures electrical conductivity between metal parts of the electrical system, such as between a metal box and a metal raceway or conduit. In a light pole, note how the bare copper conductors from the underground conduits are joined together and to the grounding connector. TxDOT requires all grounding conductors to be bonded together at every location. Bonding all grounding conductors together helps ensure that all metal parts of the equipment in the electrical system have no voltage difference between each other and the earth. A split bolt connector made of copper or bronze can be used to join grounding conductors together. The The center of the bolt has been cut out to make room for the conductors. TxDOT requires split bolts and other electrical components to be listed by UL or other testing organizations. It is important to verify that only connectors listed for use on electrical conductors are used. A split bolt is typically listed for connecting only two conductors. The grounding connection in a light pole is shown on RID 1. A bonding jumper connects the equipment grounding conductors to the metal pole base with a special type of connector called a tank ground fitting. The connector is made of bronze, and the nut and lock washers are stainless steel. All metal light poles installed on TxDOT projects must be grounded with a tank ground. A tank ground is listed for only one conductor. Using two conductors would violate the listing. Back at the service, note the grounding conductor coming out of the metal conduit. A grounding bushing provides a grounding connection to the metal conduit. TxDOT requires that the ends of all metal conduits be installed with a grounding bushing and connected with a short conductor to an equipment grounding conductor or the grounding bus. By connecting the grounding bushing, metal conduit, and grounding bus together, the metal conduit is bonded to the ground. The NEC requires that all non-current carrying metal parts, which may become energized, must be grounded. By bonding the metal conduit to the ground bus, we have complied with this important code rule. In this section, we will inspect the grounding systems of several different types of electrical installations. While no two installations are the same, many things are common to all installations. It is recommended that the Standard Specifications Book, the NEC, and the plans and specifications for the project be studied and brought to the location for reference. Taking photos of the installed equipment will help document the inspection and complete the report. Let's begin our inspection inside the electrical service. We can see that the white grounded service entrance conductor has been connected to the grounding bus. The metal service enclosure is bonded to the grounding bus with a special green-headed screw. The NEC requires that when bonding the ground bus with a machine screw, the screw head be painted green. A metal strap may be used as an alternative. The grounding electrode conductor has been connected to the grounding bus. The other end of the grounding electrode conductor has been connected to the grounding electrode with a ground rod clamp, and the connection has been properly tightened. A 5/8 inch diameter, 8-foot-long ground rod was driven into the soil, so the entire rod is in contact with the soil. A bare copper conductor connects the grounding bushing on the metal conduit to the grounding bus, bonding it to the equipment grounding system. We can also see the equipment grounding conductor continue down into the conduit. In this traffic signal cabinet, the equipment grounding conductor is a stranded bare conductor and connects to a grounding lug on the terminal strip. The other end is connected to a ground rod clamp on a ground rod driven into the soil through the concrete foundation. The ground rod is specified by standard TSCF to be at least 5/8 of an inch in diameter and at least 8 feet long. Sometimes the rod can be specified by the plans to be 10 feet long to ensure that there is at least 8 feet in direct contact with the earth. It is always necessary to check the plans thoroughly on each project to see exactly what materials are specified. At this shoe base light pole, the equipment grounding conductor is connected to the pole with a tank ground fitting. The connection should be checked to ensure that it is properly tightened. At this T-base light pole, the equipment grounding conductors come out of the underground conduit. The grounding conductors are bonded together and connected to the T-base with a tank ground connector. The fitting should be inspected to see that it is made up correctly. The tank ground connection must be tight, with only one conductor connected to it. By now, you may have noticed that an equipment grounding conductor runs to all the electrical equipment in the system. First, we saw it go to the traffic signal equipment, and now we see it at the illumination equipment. The equipment grounding conductor is used to ground all metal electrical equipment in the electrical system. Now, we will inspect a concrete barrier-mounted light pole. Inside the junction box, the inspector should check that if the box or cover is metal, has been bonded to the equipment grounding conductor with a listed fitting. All grounding conductors in the box should be bonded together. The equipment grounding conductor in the handhole has been connected to the pole with a listed tank ground fitting. Inspect the grounding connection for proper tightness. Before concrete is poured for the barrier, the concrete encased grounding electrode connections should be inspected to see that they are properly made up and tight. The inspector will verify that the mechanical connectors are rated for embedment in concrete, that a bonding jumper is the correct size, and that it is a stranded copper conductor. At this roadside flashing beacon, the equipment grounding conductor has been correctly run to the metal pole base. The connection is made with a listed tank ground fitting. Once again, ensure that the connection is properly tightened and that the ground rod is installed correctly. This ground box cover is made of metal. Metal covers on ground boxes must be grounded, since the metal can be a shock hazard. A stranded bonding conductor must be either welded to the underside of the cover or connected with a tank ground fitting. The connection should be checked to verify a single equipment grounding conductor is attached to the tank ground and is made up tight. This ground box has a non-metallic polymer concrete cover. A non-metallic cover does not need to be grounded. Inside the ground box, we check that all grounding conductors have been properly bonded together. All strands of the conductor should be in the connector and made up tightly. If a connector is loose, conductor strands could slip out and cause a poor electrical connection. Next, we will inspect a high-mast pole's grounding system at the electrical disconnect mounted on the side of the pole. Inside the breaker box enclosure, we can see that the equipment grounding conductor has been bonded to the green insulated conductor in the power cord. The power cord provides electrical power to the lights at the top of the pole. A 2-hole lug has been used to connect the grounding conductors together, and the connection is properly tightened. Now we will inspect this section of metal conduit. The NEC requires that all metal parts be bonded to the equipment grounding conductor, so it is necessary to open the service door to inspect these important connections and conductors. Check to see that a grounding bushing has been threaded onto the end of the conduit and that a bonding jumper has been connected to the grounding bus. Verify that connections are tight and that listed fittings have been used. Notice how long this section of conduit is. It runs along the length of this bridge. As the air temperature around the bridge changes, the length of the bridge expands and contracts. The bridge has expansion joints designed to allow expansion and contraction to occur. As temperature changes, the metal conduit will also expand and contract. TxDOT requires that metal conduit mounted externally on bridges be provided with the expansion joint at every bridge expansion joint and every 150 feet or less. This is a listed rigid metal conduit expansion joint. It allows the conduit to expand or contract without placing any stress on the conduit. The fitting uses an internal bonding jumper to ensure electrical conductivity along the entire length of the conduit. In this training video, we covered the importance of grounding and bonding to protect people from electrical hazards and to protect equipment from damage. Other videos in this series cover other parts of the electrical system. Each of these training videos adds to your knowledge of electrical systems by covering only one component of electrical work. This allows you to quickly master the knowledge necessary for a particular job in small parts. You are not alone. You work for a large organization with very knowledgeable people such as professional electrical engineers, master and journeyman electricians, and trained signal technicians. When conducting electrical inspections, ask for help from one of these people. TxDOT has some very good formal training classes, such as TxDOT Electrical Requirements for Illumination and TxDOT Electrical Requirements for Traffic Signals. We recommend that you participate in these training programs. If you do not understand any portion of this video, ask your supervisor for answers to your questions. You should never be too comfortable or complacent with electricity. That is when it catches up to you. The inspector is often the last line of defense between improperly grounded equipment and the public. Remember, safety first is a must, not an option.